Is it working?
Yeah, that should all work.
Oh, great. Okay, thank you. So, basically, like last time at the end of the course, at the end of the lecture, I defined like some version of the sheaf theoretic version of motivic complexes. And I think, I can't remember, but I defined it as so we constructed the bounded from the right complexes of Nisnevich sheaves with transfer. And I think I defined this guy as the quotient of say, homotopy invariant sheaves with transfer. But I think like this technically could work as a definition, but it's not quite the order in which like at least Vygotsky did things. So like at this point, let's like make a slight correction. So I want to define dm, so the motivic complexes, as a subcategory of Nisnevich complexes of Nisnevich sheaves with transfer, whose cohomology sheaves are homotopy invariant. So recall homotopy invariant just means that f of x is isomorphic to f of x times a1 via the canonical projection morphism. But like the point of at least the first part of today's lecture is to prove like essentially that these two definitions are the same. So they're the same, and I guess that's the contents of the so-called localization theorem. In the same way where if you have a category of three sheaves, I can also define the category of sheaves as a subcategory which satisfies some kind of gluing condition. But on the other hand, there is some kind of sheafification. So yeah, the category of sheaves is also a quotient category of the category of pre-sheaves, you know, in some kind of sheafification criteria. So we need to like connect, some subcategory and some localization, and the bridge, like to do this, is basically we need to. So for sheaves, it would be like some sheafification, but here we're dealing with kind of complexes of sheaves. So we want to basically kill A1 cohomology. That's what this kind of bridge will be. So we should consider basically some analog of singular complex. And in this kind of framework, this is called the Suslin complex. So that's my kind of next definition. So definition. So yeah, just so everything is clear, the aim of the game now is to show that this subcategory is the same as a localization. And the reason for doing that is we want to compare, recall our kind of geometric motives with these guys. Well, with this one. and the geometric motives was defined using some kind of localization. So it's natural to compare this one to some kind of localized version. So then it will be easier to compare this localized quotient with the quotient here. Okay, so Suslin complex, but just think of this as a singular complex or cochain complex, which is complex, I guess, in this because we're doing homology, in this framework of motivic complexes. So let's define. So we have this simplicial presheaf. So defined by delta at n will be just the affine line, but I write it like this, the affine space. There are face maps here. So delta I going from capital delta n to capital delta n plus 1 defined by setting xi equals 0. Okay. I just recalled that like last time I defined the category of motivic complexes to be maybe some localization category, but it will be correct, but like it's not quite the right order of things. Like the way Vygotsky did first was to define it as a subcategory whose cohomology sheaves are homotopy invariant. And it's kind of more, anyway, that's what Vygotsky does, and the content now is to show that it's the same as the quotient category. I guess my thinking was to do it straight away with the quotient category, to make this definition, because I wanted to like quickly make it compare it to the geometric motifs. So, yeah, President Babic, right? Okay. So, with this kind of affine space, if I have F, a free sheaf with transfers, then I can define this free sheaf with transfers. So another. So define another free sheaf with transfers. Oh yeah, and now what I'm doing now is like defining some version of singular complex in the setting of motivic complexes for, this is called the Suslin complex. Another presheaf with transfers, so defined by Cn of f, sending, evaluated at some test object x to be just f of x at delta times delta n. So it's similar to what's going to be, happening with singular homology, I guess, in algebraic topology. And I can put these things together. So there is a complex C lower star of f with maps, so Cn of f to Cn minus 1 of f by the natural thing, which is what you do in algebraic topology, I guess, is the alternating sum of the face maps. Maybe I write that a bit clearer. Okay. Okay. So, as like one should expect, like this this object, like this Suslin complex. So this is the Suslin complex, I guess. singular chain complex. But in the derived category, I mean, this sits maybe inside D minus of the derived category of the Nisnev sheaves with transfer. So in the derived category only cares about homology in some sense. So two, I mean, things which are quasi-isomorphic have the same homology. And we kind of expect that like this Sussman complex, I mean, the cohomology of the affine line, higher cohomology at least, vanishes. So we expect that this will be like the object in the quotient category of this guy. So it should live naturally inside one side quotient out by homotopy invariance. But anyway, the right statement is as follows. So we have this map, so proposition. We have this map C star, which takes some, let's say, Nisnevich sheaf with transfer. And a priori, it lands inside, it's a complex, right, of Nisnevich sheaves with transfer. And what I'm saying is that it naturally factors through our motivic complexes. Sorry. I mean, first of all, there's this, like, I hope this kind of makes sense with all the objects that are defined so far. I mean, this is literally this guy is a sub-category of that. And all that this proposition is saying is that, essentially, like, if I was to say it in one sentence, like, cohomology of A1, or higher cohomology, vanishes. So that's why it factors through, to homotopy invariance. Okay, so I guess I just give a sketch. So this guy was defined as complexes whose cohomology sheaves were homotopy invariant. And basically by, let's say, unraveling the definitions, one can show that this Sussman complex has homotopy invariant cohomology pre-sheaves. So I won't do that like on the board, but it's in the notes. But we need to show that the sheafification of those pre-sheaves are also homotopy invariant, and here comes in like a major kind of step in Vygotsky's work, I guess. So the theorem is it's kind of it's due to Vygotsky, as many things are, I guess. But some of these ideas, by the way, like Sussman complex and things, were considered before Vygotsky. Vygotsky, let's say, he uses pre-theory, like theorem is basically say if F is a presheaf with transfers, which is homotopy invariant, so this theorem, like, it was done like before fixing, I guess, the right topology, which is we're working in the Nisnevich topology here. But I guess like the first natural topology is the risky topology. So in any case, like you can consider the F zar, which will be, so this presheaf is going from the category of correspondences, but F zar, we can restrict F to be basically on the smooth spaces, and just as a risky sheafification. So this F zar, it doesn't live on the whole category of correspondences, but just on the smooth schemes, so smooth separated. And you can still talk about homotopy and variance in that setting. I mean, you're just worried about whether the projection map gives an isomorphism. So the statement is that then is F zar is homotopy invariant. And then, furthermore, so our sheafification with respect to the Nisnevich topology, which lives on the whole category of correspondences, of finite correspondences, restricted to smooth schemes, is the same as this F Zariski. So like somehow this notion, whether you like sheafify with respect to Zariski or with respect to Nisnevich, they're called like, I think as far as I understand, they're called like different pre-theories in Vygotsky's terminology. And this theorem is saying like all these pre-theories are kind of the same in some sense. But anyway, the upshot is that like these cohomology presheaves of the Sussman complex, they, due to this theorem, we sheafify them, and they are also homotopy invariant. But yeah, I of course don't prove this because I feel like it's a bit technical. I mean, it's not. Yeah, I don't want to say too much, but anyway, Vygotsky spends quite some time doing this in one of his papers in that big book by that's 3 authors published in around 2000. Okay. So now we can basically state the localization theorem. So so we have this functor C star, which now we know goes from the category of Nisnevich sheaves with transfers to, thanks to the previous theorem, homotopy invariant guys. I guess like it's not, I mean, it's just formal nonsense to extend this to the derived category itself. And let's call this guy R C star, I think that's how I donate it, yeah. And basically, the content is that this theorem is, this functor, RC star, identifies with the quotient map, or quotient or localization map, from D minus of the Nisnevich sheaves with transfers by sheaves which are homotopy invariant. So okay, so let's try to prove this, I guess, or give some ideas at least. So, like, we've just used the Sussman complex to basically give the, I mean, if this was like the category of pre-sheaves and the category of sheaves, it's some version of sheavification, but here we are not killing like open sets, we are killing A1 cohomology. So the analog is to use singular chain complex. So this is just killing A1 cohomology, but yeah, it will be, this functor is basically the left adjoint of the inclusion map. So in the same way that sheavification is left adjoint to the inclusion map. So what do we need to prove here? So first statement I want to show is the following. I think maybe that's the only statement we'll show. So for any object T, so for T in my category of motivity complexes, and B, let's say, to be the complex ZTX times A1 to ZTRX. So this is a complex viewed as an object in D minus of Nis. I want to show that, like, want to show that the homomorphisms in D minus of Nisnevich sheaves with transfers of BT is 0. Okay, so what does that give, for example? What does that give? It implies, so this implies that DM of motivic complexes to the quotient category is fully faithful. Okay, just in case, like, I recall, like, what the homomorphism sets are in a quotient category. So, like, for example, if I have some category C and I have some subcategory I, which is typically like a thick subcategory. If I want to take quotients, then my home sets in this quotient category, say from x to y, by definition, so the objects will be the same. And thinking of x, y as object in category C, they are the co-limit of, here I think of C as a triangulated category. Hom of C of x prime to y, along where the limit takes place along all morphisms x to x prime, such that x to x prime, the cone of this guy, which makes sense because we are in a triangulated category, is in I. So essentially you are just like killing all morphisms whose kernel and co-kernel are in I, essentially, or making them an isomorphism. But this is like the formal way of saying it.
На их не надо написать какое-то условие, я так понял, это типа локализации в смысле с, но там у с же еще справа что-то берется под объекты Y, там не надо полностью какой-нибудь.
In Say's quotient category, there's some object y.
I mean that is like say localization in abelian category.
I mean, so here, like, there is such a notion of abelian, of Say's quotient category, but here, like, my setup is a bit different, so I don't have a abelian category here.
Yeah, but we don't have to do something with direct limit.
But you think I don't have to take a direct limit?
Like we change x by x prime, but don't change it.
Yeah, we don't change y. Yeah. The reason is that like so this guy here, it's kind of like hom C of the limit of, I guess, maybe I should put x prime here, sorry, it's not right. Along all objects x prime to y. I mean, yeah, like formally, like the co-limit becomes a limit once I put it inside, in some sense, if I was allowed to do that, suppose. And I'm kind of, along all objects which map to X, I want to kill the kernels and co-kernels of those guys in this kind of way.
So killing cones implies killing co-cones, yes?
Yes, yeah. And I said, strictly speaking, I think of a cone as like the datum of a kernel and a co-kernel. I like in the, maybe if it was just exact sequence, like literally that would be true. So anyway, like with this, like this definition, like I mean, which I hope you guys had in mind before, because I was talking a lot about like quotient categories, but I just wanted to make explicit that like once I have like I'm quotienting out by these objects basically, or the thick subcategory generated by these objects. And of course, the thick subcategory is just basically direct sums and sum ends of those things. And by triangulated category kind of nonsense, you can just, well, once all these homes are equal to 0, that means that if I take, in this colimit will be trivial and it'll just be just this thing. Because if I write out the triangle of this thing, let's say B is in here, then I take the hom of this triangle, I get I get another triangle, and I'm saying like, since the hom of BT of this guy is 0, that means the hom of x to x prime to y, or in this case, x prime to t, using this one, and x to t, they will be the same. So this limit basically becomes trivial, and you just get back like a fully statement that's saying that this funct is fully faithful. Okay. So let's try to show this fact here. That's, as I've written on the board, that if I have some complex coming from homotopy invariance, basically, then this statement is true. So basically, like, I mean, hom in a derived category, we're essentially looking at, I mean, this statement, if I expand it out, what I'm really saying, roughly, is like the hom, I'll drop like the writing this guy out, but the hom of, say, ZTR x times A1 of t is basically isomorphic to the hom of ZTR of x of t. So this statement here is basically rewording star, this one, just by writing our triangle. So I need to understand what these homs are. And homs in the derived category is basically higher x's, at least like when t is an actual sheaf. So basically, I need to prove something relating the x's to, it would be nice to have some relationship between higher x and say some cohomology. And the statement is as follows. So for F, a Nisnevich sheaf with transfer, then the hom in my category, or the higher x's of, say, ZTRX of F is the same as Nisnevich cohomology. So the higher x. Okay, so there's something going on here, like it's not formal. I mean, what would be formally true is like this guy here, so is formally, by some just like derived category nonsense, that's the same as x, but not in the category of Nisnevich sheaves with transfers, because Nisnevich sheaves, like the Nisnevich cohomology doesn't see transfer structure. Like that's something a bit bigger. But it just sees like Nisnevich sheaves, let's say, the category of Nisnevich sheaves. So this is something that doesn't have this transfer structure coming from finite correspondences. And like, strictly speaking, this transfer sheaf was, if we just maybe restrict it to Nisnevich sheaves or something, some some free sheaf. I'm just going to write ZX. So this is true, but something here, like this is a bit more, like this equality is not formal. So there's something to say. So the first step is that for I equals 0, this is just your netta. So everything is easy when I equals 0. I mean, yeah, ZTRX was just the free sheaf on correspondences, so you easily get back that homomorphisms from ZTRX to F is just sections of F. Okay, that's just your netta. So suppose I greater than 0. Now, in the previous lecture, we basically showed that like this category of Nisnevich sheaves with transfer was a Grothendieck category. So in particular, it has enough injectives. So we can take an injective resolution. Of F. And now what we have to show is that for I, an injective object, in my Nisnevich category with transfers, that's HI, then its Nisnevich cohomology is 0. So I haven't done anything like, I've only done formal things so far, so nothing special. Just reducing to injective objects. And I can do that because I have a Grothendieck category. So of course, like if just repeating like the analog of this formal equality here, like if I was an injective object in the category of just Nisnevich sheaves, then this would be like formally true, trivially true. But I have something else.
You need to prove that injective objects are acyclic when you remove transfers.
Exactly, something like that, yeah. But anyway, we can use Čech cohomology. So, so we have to show this for I greater than 0, by the way. Yeah. So it suffices to show that for U to X Nisnevich cover, that the complex 0 IX to I of U to I of U times X U, and I just write one more term just in case. Is exact. So if you prove like this Čech sequence is exact, then you get high cohomology is 0. This is just maybe like a precise statement can be found in the Stacks project. But this is kind of standard arguments. But now, again, by using your netta, each of these guys is basically the hom in my Nisnevich category with transfers of this IXA is just the hom of ZTRX to I. And similarly, like, and so on. Like, for example, this is the hom of ZT of U times X U or I, and so on. And I is an injective object. So I injective implies that the functor hom is exact. So in summary, it suffices to show the following sequence is exact. So it suffices to show ZTRX ZTRU. So RU times X U and so on is exact. Okay. So up to now, so far, like everything has been formal, but we have anyway reduced to something on some statement involving just the representative shift. But so far formal. But now, like, we really use Nistovich topology. So, so we need to show this is exact, by the way, as Nistovich sheaves. Yeah. So, so the category of Nistovich sheaves has enough points, so it's enough to take stalks. So, basically by taking stalks, so this is equivalent to having the following sequence of say SI. So I just consider basically some Henselian, i.e. some Henselian neighborhood as a limit along some schemes, SI. Sorry, SI. So equivalently, like this looks like if I just call this Henselian neighborhood just by S, then it suffices to show the following sequence is exact somehow. So this correspondences evaluated at S. So strictly speaking, like this ZTR sheaf was defined on the category of correspondences, right? Which are smooth schemes. So this Henselian scheme, like, is not going to be smooth anymore. But like, we can just think of it as like a formal colimit and still think of it as like correspondences over S, finite correspondences over S. So we need to show this is exact. So now, like if we take the first term here, so first term is this ZTR of XS, right? So by definition, this is so finite correspondences from S to X. So they're finite over S, which is good. And I can just take some Z in here. So this will be some subscheme of S times X. So finite over S. And so I can consider basically L of Z of S to be just a abelian group maybe generated by Z. And so this complex 1, like 1 then is a co-limit of complexes of the form 0 to L of ZS to L of Z of U over S, where Z of U is equal to Z of times X over U, say, and so on with higher terms. But now, like, S is Henselian and Z is finite over S. So as like the usual trick from last lecture implies that like Z is a disjoint union of Henselian rings, basically. And furthermore, like Z of U to Z is a Nisnevich cover. Wait. So because Z is just a disjoint union of Henselian rings, this Nisnevich cover splits. So this gives some morphism like this in the opposite directions. And then it's like an exercise to show that these morphisms give up a homotopy between this complex and the identity map between this complex and the zero map between it. So yeah, anyway, like the hard work has been done, and now it's more formal work to conclude that like these splittings show that this sequence is exact. So yeah, maybe I just write that down. The splittings give a homotopy between, say, one, identity map of 1 and the zero map. Where 1 was the complex that I erased from this board. So the upshot is that like 1 is exact. Okay. So yeah, I mean, in summary, we just proved like that that like this proves. Like, let me just remind you, just because I removed it from the several boards ago, that like D, the lotidic complexes, quotient category, which certainly exists. Is fully faithful. Okay, to prove to finish the proof, to prove essential surjectivity. Well, let me just say that you need to use, you need to do more work first of all, and in particular you need to use some tensor structure on D nis. So to prove surjectivity, basically the statement is, to prove essential surjectivity, you need to show that the canonical map from F to the Sussman complex is an isomorphism in the quotient category. But anyway, let's just leave it there. I think we can move on to other things. I think this gives a good idea of what is going on. Are there any questions or something? Okay. Let me continue then. So now I go to the embedding theorem. So I will use the localization theorem now to state the embedding theorem, which basically will allow us to move from geometric motifs to motivic complexes. So maybe just one remark. This category D of motivic complexes is pseudo-abelian. So recall this means that every projector or projection map, which means p squared equals p, has a kernel and co-kernel. That's that's asking something. I mean, this is certainly not anywhere abelian, this triangulated category. But the point is that a triangulated category is pseudo-abelian if it is closed under countable direct sums. And in this case, so this is you can find this in the Stacks project. And in this case, it's it's not difficult to check that something that's homotopy invariant, you can just add it many times and it remains homotopy invariant. So yeah. Anyway, this is basically to help us compare with geometric motifs, because geometric motifs, we took the pseudo-abelian completion. So I can now state embedding theorem. So this is the second big theorem after localization theorem of Vygotsky's work of motifs. So yeah, I'm gonna build up the diagram. It will be like some diagram. So I have my category of finite correspondences over K, and I can take the representative sheaf associated to that, and I land in some category of Nistovich sheets with transfer. So this is like what we've constructed so far. Then basically by formal nonsense, I can upgrade this functor to one from the bounded homotopy category to the derived category, say from minus. Yeah, I mean, could also, yeah, I mean, this minus here is purely because we are working with like co-chain complexes, chain complexes, which could theoretically be unbounded from to the left, but in practice bounded. But anyway, it's typical to work with D minus when one works with homology chains. And bounded, yeah, we just took, yeah, from the point of view of like geometric motifs, we were not really interested in homology at that point. So yeah, it was enough to just take KB here. In any case, like we can quotient out by Mayer Vietoris. So this is the usual construction. So quotient out, quotient by Mayer Vietoris plus homotopy invariance. And we land in our category of geometric motifs, right? Which we constructed 2 lectures ago, which absolutely has no understanding of like what sheaf is or anything like that. And also like the content of the localization theorem was that this functor basically of taking Suslin complex, or the derived upgrade of it, we land in the category of motivic complexes. So these are guys equipped with sheaf homology theory or cohomology theory. So that was, say, localization theorem. And now the content of the embedding theorem is that like this, there exists some functor here. So there exists a fully faithful map here, which makes everything commutative as functors. So the upshot of this theorem is that like now, like when we can, if we have geometric motive and we want to prove something here, we can kind of upgrade it, not upgrade it, but move to a bigger category, this equipped with sheaf homology theory, which in practice is maybe more powerful. So that's the upshot of this. Okay, so let me give some sketch of it. So in some sense, like, I mean, the theorem should basically be obvious. I mean, in both sides here, where we've set it up so that like we are quotienting by something. And also, we've proved in the previous lemma that this guy is pseudo-abelian. Like, we don't need to take pseudo-abelian completion there. There is this annoying thing of that we quotient here, and then, like, I didn't write it here, like, plus and like take pseudo-Abelian completion. But if I have some functor from some category A, some additive category or something, some fully faithful functor, to some pseudo-Abelian category, then basically by like formal nonsense that this pseudo-Abelian completion, there is an induced functor from the pseudo-Abelian completion of A to our target category T, and moreover it remains fully faithful. So to prove fully faithful here, we can essentially forget about taking pseudo-Abelian completion and just think of quotient localization, which is good. And somehow, like now, it should be fairly obvious that this map exists. I mean, here we are quotienting by homotopy invariance, and also here we are quotienting by homotopy invariance. But here we're also quotienting by Merviatoris. So we just need to check one thing. For existence, we should check like what happens to these Merviatoris sequences. So given some Merviatoris sequence, so given U intersection V to U plus V to X, a Merviatoris guy. So this gets sent to ZTR of U intersection V. I mean, it gets sent, we haven't constructed a map here, so we don't have a map, but we want to construct it. So it should get sent to something along ZT in some sense. To ZT of U plus V to ZTRX. And the good thing is like, this is exact. Exact by the general result that we proved by previous result, where we had long exact, where it follows from exactness of the more general situation, basically, where I have like some Nisnevich cover. And so on. But of course, like in that sequence, you have many terms, but they will be zero in this case because you can't take more intersections than two terms. So this will, land in something in here, and because this is exact, we get something in here. So basically, like, this gives a definition of this functor I. Okay, and to prove fully faithfulness, like, we should think of like how ZTR works. So ZTR is not fully faithful. So like we can't, here we're taking sheaves, there's pre-sheaves here, so there's some localization going on. But actually the localization of Merviatoris somehow, well, it's not happening here, but it's happening along here. Like, so to be more explicit, this ZTR map, it's a map from the category of homotopy invariances, but it originally factors through the derived category of pre-sheaves with transfer. And then, of course, you localize by sheaf condition to land in this D minus of Nisnevich. And basically this functor here, by some derived version of Yoneda, is fully faithful. And essentially, like, if I call this map, say, J, then basically I is equal to, say, J quotienting out by homotopy invariance plus some sheaf condition. So yeah, it remains fully faithful. So the upshot is that I is fully faithful. Yeah, maybe to write it out formally, like it takes a few more lines, but that's what's going on here. Okay, so now we can compute some things. So I want to discuss like a consequence of this embedding theorem, but we need to do some preliminary work first. So the first lemma is the projective bundle formula. So most of like the formal, not the formal, but I would say the grinding work is like kind of finished for now. So we get to do some calculations. I don't know what you consider like grinding work or whatever, but so the formula is as follows. So let X be some smooth separated scheme over K, and E be a vector bundle over X. Then we have the associated projective bundle over X attached to E. And so there is an isomorphism of the motive, the geometric motive associated to this projective bundle with just direct sums over the motive or the geometric motive associated to X, and twisted and shifted in appropriate places. So this generalizes like what happens for the formula for projective line when X is a point and things like this. Okay. If you don't know like what a projective bundle is or like what this PXE object is, then that's okay. So I think it's enough to just take X to be a point and E to be some vector bundle. Then like this P of E object, you should just think of it as like some kind of symmetric product of E's. Okay. Most of the calculation actually will be in the trivial case. So basically by taking like by trivializing E, our vector bundle, which means take a neighborhood, take a covering where E becomes trivial. Then using Merviatori's triangle over and over again. I mean, Merviatori is basically, if I have like my trivialization to have two terms, say U and V, then Merviatori's is basically M of U intersection V. I have like some triangle, right, from Merviatori's. And on these guys, like on this object, E is trivial now. So because two of the terms, like if I can prove the theorem basically for two of the terms, then the second term will follow as well. So the third term from basic triangle nonsense. So by trivializing E and looking at Merviatori's, so can assume E is trivial. And in this case, P of X of E is just equal to the projective space of dimension E times over X itself. And then, yeah, by looking at, say, how M's...
Of dimension E minus 1.
But you think this should be E minus 1? But if E is, say, O, then I just should have P of 1, right? Really?
Well, so projectivization of line is a bit, of course. But
I'm not sure. Let me think.
it's not important.
Yeah, I guess
So
it's...
sum is up to dimension E minus 1.
Yeah, this sum is here, but I think in this case...
So...
Yeah, I mean, for example, if I have P of 1 here, then... yeah, maybe you're right. Yeah. I think you should have E minus 1 here. I think. Yeah, because otherwise, yeah, you don't have enough terms for P of 1. Like you should have Z plus Z1 of 2. You're right. Okay, so then by yeah, now I'm confused actually whether the motive of products is also a product. I think so, because every functor in the embedding theorem was tensor functor. So in any case, like, can further assume X is just a point. So we need to show that basically suffices to show M of P of N is equal to the sum from I equals 0 to N, I guess, yeah, of Z of I, 2 of I. So I mean, then I get the mx factor here just by tensoring everywhere in general, right? Yeah. Okay, and here there's like many tricks to do. So I don't know, like in one lecture, I think maybe lecture 3, I stated like some projective bundle formula in the setting of Chow motives. There was no like twists, there was no shifts, of course, because there was no derived category. But anyway, some formula like this I stated, but I can't remember whether I actually, it's in the lecture notes, but I can't remember whether I actually did it or not in the actual lecture. So there's a bunch of covers that we need to consider. So the first cover is something like this. So we're going to use Meyer-Vietoris several times. So we can write P of n as the A of n union with P of n away from 0. By applying homotopy invariance several times, we know that M of A of n is equal to M of a point, which is equal to Z by our definition of Z. And also P of n minus 0 lives over P of n minus 1, and all the fibers are A1, so this is actually an A1 bundle. So this implies by homotopy invariance that the motive attached to P of n minus 0 is the same as the motive attached to P of n minus 1. Yeah. So basically, by like induction, I mean, we know that this is Z, the motive at least, and we know that this is like basically P of n minus 1. Yeah. Yeah, at least, yeah, by induction argument on n, we get that the motive attached to P of n minus 0 point is the formula up to n minus 1. Okay. But we also, in the Meyer-Vietoris, we also take intersection, right? So we have like, yeah, if you can imagine the Meyer-Vietoris sequence, we have information of this guy and this guy, but we also need intersection. And the intersection is as follows. So we also need to understand motive of the intersection. And for some reason, I have written down here that this intersection is just an minus 0. I mean, this intersection here. That seems right.
I'll be back.
Что, мне можно тестировать все, я так понял, не так? Себе. Ну, Каледин все ничего не будет. Каледин взял. Каледин завтра.
Yes, значит,
Каледин будет завтра. А следующий четверг.
Sorry about that. I have something stuck in my throat.
Okay, so we need to calculate the motive attached to this. And yeah, this statement is that this is this an minus 0 is z of n, 2n minus 1 plus z. So I think we're out of time, but I think there's some more induction argument to do here. So plus more, I mean, to prove this, so you need to take more covers of an minus 0. But we can finish that next time. Thanks. Jiping, how do I finish this?
Це,